Hi, I'm Dave Mueller, retired hydrologist from the U.S. Geological Survey and founder of Genesis Hydrotech. In this session, we're going to talk about the bottom track, GPS, depth, and water track tabs in QRevInt. To discuss the bottom track, GPS, depth, and water track tabs, I have loaded a M9 measurement from the 1-ECTI folder. Let's begin by looking at bottom track. Bottom track automatically applies three different filters: a three-beam solution filter, an air velocity filter, and a vertical velocity filter. This current measurement has no three-beam solutions. They are all four-beam solutions. So if we take a look at data from a different measurement, we can see that in this plot, there are some three-beam solutions and also some solutions where there were no valid beams collected for bottom track. For a three-beam solution, the automatic algorithm will interpolate from the nearest four-beam solution a value for the ensemble with a three-beam solution. If the three-beam solution is within 50% of that interpolated value, the three-beam solution is deemed to be valid. If that three-beam solution is different by more than 50%, that three-beam solution is marked as invalid, which you see here with the red circles indicating invalid data. Next, we'll look at the air velocity. This is an M9, so we have multiple frequencies, a 1 megahertz and 3 megahertz for bottom tracking. And you'll see that in the shallower depths, the green plus marks indicate that bottom tracking was using the 3 megahertz beams. And then for the remainder of the transect, it used the 1 megahertz beams. The air velocity filter is based on a statistical assumption that the air velocity should follow a normal distribution, and the goal is that we only want to mark obviously invalid data. The air velocity filter uses a threshold of 5 times the interquartile range. Any data that lays outside the 5 times the interquartile range is marked invalid, which you see with 2 points here that are well beyond the scatter of the rest of the data. The vertical velocity uses the exact same filter algorithm, being 5 times the interquartile range, even though it could be possible that the vertical velocity wouldn't follow a normal distribution. However, those would be some unusual river conditions. So again, we have just 2 points that failed to meet that criteria and are marked invalid. Those 3 filters are on automatically, but they can be changed. For 3-beam solutions, the user could allow 3-beam solutions or decide that only 4-beam solutions are acceptable. For air velocity, the user could manually enter a threshold of their choosing. In this case, we'll choose 0.005. When we apply that filter, we will see some additional data marked invalid. When automatic is applied, each of the different frequencies are treated independently. However, when a manual filter is applied, that is applied to all of the frequencies or all of the ping types that are present in that particular transect. These filters are also applied to all of the transects involved in the measurement. It is also possible to simply turn the filter off. Likewise, the same options are available for vertical velocities. We can leave it on automatic, we could manually set a threshold, or we could turn the filter completely off. Changing from automatic to one of the other settings will show the blue tab, the BT, in blue, indicating that a change from the automatic settings has been made by the user. The other filter is seldom used, and it is a smooth filter based on a lowest smooth and a dynamic window. We can see here the blue line is the lowest smooth, and then an algorithm is used to fit a high and low threshold based on the scatter about that lowest smooth, and then any data that would lie outside the gray shaded area would be deemed invalid. This particular filter takes time to process and is typically not used unless the air velocity, vertical velocity, and three-beam solution filter do not remove the invalid data as deemed by the user. Finally, we can look at the source, and we see that the majority of the ensembles for this measurement are referenced to bottom track, but where we had invalid data marked by air velocity or vertical velocity or a three-beam solution, we see that we've done an interpolation. However, this last one says that it's invalid because we always interpolate, but we do not extrapolate. And this last value was the last ensemble, and it was marked invalid due to the vertical velocity. And you'll notice that both of those were also marked invalid by the air velocity. The table at the top shows what percentage of data are marked invalid by the various filters. You can look at each individual transect by simply clicking on the file name, and it will plot that transect. The plot at the bottom is just a simple time series of the boat speed, but where you see letters such as this E and this E and this E, those mark invalid data where they would have plotted without interpolation. And the E references air velocity. It could be a V if it was a vertical velocity. Looking at the source radio button, we see that most of this transect was referenced to bottom track, but where we had invalid data, linear interpolation was used. It is possible, because we have GPS data, that we could use composite tracks. However, our GPS tab is shown as red, so something must be wrong with GPS, so we would not want to pick composite tracks until we check out the GPS tab, which we'll do now. The first thing we notice looking at the GPS tag is that the GGA percent invalid and differential quality invalid is all marked red and is at 100%. And as we look down at the quality plot, all of the data have a red circle around it indicating that they're invalid. By default, QRevInt requires that the GGA string must indicate that it has been differentially corrected. However, for this data, we see that the quality indicator is 1, indicating that it is an autonomous GPS solution. We can modify this setting by clicking on the drop-down menu and selecting autonomous. When we do that, we see that now all the GGA data are in fact marked valid, and we can see the blue GGA ship track in our ship track plot. The next quality we can look at is altitude. The altitude check is based on the assumption that the vertical accuracy of a GPS is approximately 3 times worse than the horizontal accuracy. Since we typically want to see at least sub-meter accuracy, we can look at the altitude, and if the altitude changes by more than 3.5 meters, we can assume that we are beyond our sub-meter accuracy for horizontal accuracy. For this particular measurement, all of the data are within plus or minus 3.5 meters of the mean altitude. However, we can look at another data set and see that that threshold was exceeded, and looking at the time series plot of the boat speed, we can see a line here and all these A's where all this data was marked invalid and thus was linearly interpolated. Moving on to h-stop, we see that for this measurement, the h-stop is typically less than 2. The requirement, or the threshold, for our h-stop is that it should be less than 4. While we can look at the number of satellite changes, we do not have a particular filter for the number of satellite changes. This is just an informational plot, and sometimes we can see if we have a jump in our boat speed or change in altitude or h-stop, we can correlate that with a satellite change. Again, the filters are on by default, except just like in bottom track, the other or the smooth filter is off by default. Just as we changed the minimum quality for GGA, we could change the altitude either by setting a manual value or by turning it completely off. Likewise, we could change the h-stop by setting a manual value or turning it completely off. Like the bottom track tab, the table at the top shows the percent invalid for each of the filters. And clicking on the file name, we can change which transect is plotted. There is an additional tab here under the GPS tab, GPS minus BT. This tab is useful for a couple of things. The first is that there is an automatic filter that looks at the lag between the GPS and the bottom track. And if that lag is greater than 2 seconds, it is going to flag a warning. This particular measurement, all the lags are about 1 second. However, if we look at an additional measurement, we can see substantial lags in this measurement, and you can see in the time series plot how the bottom track changes prior to the GPS change. Thus, if we were using GPS, the water track data would not be well correlated with our boat speed data determined by GPS. The other values in this table, the BMG minus GMG, GC minus BC, BC over GC, are explained by this illustration. If we have our bottom track course made good, or our plot, and then we also have our GPS course made good, the BMG minus GMG magnitude is the distance between these two endpoints, and the direction is the direction of the vector from the GPS to the bottom track endpoint. The angle between those two is the GC minus BC, and the BC divided by GC is the ratio of the distance made good based on bottom track and GPS. Now let's go back to our data tab. We'll click on source and see that we're still using bottom track for our main navigation reference, and we have a couple of interpolated values. Having looked at our GPS data, if we decide that it is good GPS data, now that we've changed from differentially corrected to autonomous, we can make a decision and try composite tracks. We can go to the toolbar and click composite tracks on. And we see that now those invalid bottom track data, rather than being interpolated, are being estimated from the VTG data. This table shows how composite tracks are applied. If bottom track is preferred and it is invalid, it uses VTG. If VTG is invalid, it will use GGA. And finally, if GGA is also invalid, it will interpolate bottom track. If GGA was the selected reference and it was invalid, it would use VTG. If VTG was invalid, it would use bottom track. And if all the others were invalid, it would use an interpolation from the GGA data. Likewise, if VTG was the selected reference and it was invalid, it would automatically use GGA, then bottom track, and if neither of those are valid, it would interpolate values from the VTG data. Before we look at the depth tab, I'd like to begin by describing the smooth filter, which we've mentioned in both the bottom track and GPS tabs as a filter that is not turned on by default and is generally not needed. However, this smooth filter is the primary filter used to evaluate the depth and identify invalid depths. And this filter is applied for each beam independently. So first, a robust low-S smooth is fit through the data. In this case, this is the red line that you see in the graph, the blue line being the actual measured depths. For each point, we compute a window around the data based on the variance of the nearby data points. We use a width for the lowest smooth of 20 points, and then we base a window on the interquartile range using 10 points on each side of the point in question. So identifying this point, we would count 10 points to the left, 10 points to the right. We would compute the interquartile range. We would multiply it by plus or minus 15, and that would define this dynamic window that is shown in gray. Any data that lies outside that gray window, such as this point, is marked invalid. Once the invalid data are marked, this process is repeated 3 times. This approach works fairly well where the data are consistent, but as we look at the depth tab, I'm going to show an example where the depths are inconsistent, and where they're inconsistent, this filter struggles because of the dynamic window being used. Clicking on the depth tab for this measurement shows that the depths are very consistent for each transect. So to illustrate the power and the utility of the depth tab, I'm going to switch to another measurement that may be a little more interesting when looking at the depths. I have loaded a different measurement that we may find more interesting in regards to the depth tab. We noticed initially on the main page here that the depth appears to be very sporadic along the left bank. It kind of appears that we may be coming up into the floodplain slightly along this left bank, and even to some extent on the right bank. So let's take a look at the depth tab. The table at the top shows the number of ensembles, the percent invalid for each of the beams. It allows you to click on the file name, as in other tabs, to change the transect that is plotted in the plots below. The table at the top is also where the user could adjust the draft. Clicking in the draft column will open a dialog and allow the user to enter a different draft. They can apply that to all transects or to only that transect. However, if the draft is changed for only 1 or 2 transects, there is a quality check in QRevInt that looks to see if all the drafts are consistent, and if they're not, it will issue a caution. It also checks to see if all the drafts are greater than 0. If not, it will create a warning. The settings on the right show that we can change the depth reference. We could select a 4-beam average, which would use only the slant beams and compute the average from the 4 slant beams. We could use a composite with the 4 beams being preferred, meaning that if the 4 beams compute a valid depth, we will use that. If all 4 beams are invalid, then we will use the vertical beam. We could choose just to use the vertical beam, or we could use composite depths where the vertical beam is preferred, and it would be used unless it is invalid. Then it would be the 4 beams that would be substituted. In all situations, if whatever is selected, nothing is valid, linear interpolation is used for that particular beam. We also have an averaging method. We talked about this when we discussed some of the key principles, and by default, QRev uses the inverse depth-weighted average, which we feel provides a better depth near the center of the ADCP when it is positioned on a slope, such as coming up a bank. There is only one filter setting for the depth tab, and unlike the bottom track and the GPS tabs, where the smooth filter was off by default, here it is on by default, and it is our primary filter. So let's look at the first graph. To the right of that graph, we see individual beams with checkboxes. We can turn on and off the different beams to get a better idea of what might be going on with our depths. This can be quite useful, particularly when we have highly variable situation that we have on the left bank. One of the things we see is beam 3 seems to be a little deeper and more consistent on the left bank, but shallower on the right bank. That is probably indicative of the direction that that beam is pointing. It is likely pointing towards the right bank, so that it is pointing down towards the channel on the left side, thus getting a deeper depth, and pointing up towards the bank on the right side, thus getting a shallower depth. We also note the high variability on the left bank. And even if we turn on vertical beam, it is also highly variable. The reason for that, I believe, at this site, having not made the measurement myself, is that it appears that the flow has come up into the floodplain, and they have maneuvered the ADCP into the shallower depths in the floodplain, or perhaps it is a shallow panhandle along the left bank, and there is vegetation in that area. It could be living vegetation, it could be woody debris that is laid along the shore or on the stream bed, and therefore the acoustic beams are hitting that vegetation or woody debris in various places. So sometimes it misses it and it hits the bottom, sometimes it hits a branch or leaves and it gets a shallower depth. It is in these situations that the smooth filter really struggles. Because the data are so variable, when it computes the window, the dynamic window, each of these big jumps gets included in the computation of the interquartile range, and therefore the dynamic window becomes rather large. And it's often very difficult then to determine what is invalid and what is valid. In this case, it is probably the depth is actually along this line, and this is all the effect of vegetation. But the automatic filter struggles with that computation. When we look at the graph at the bottom, this is the result of whatever we have picked for our depth reference. In this case, we've selected composite 4-beam as our preferred option. We can compare that to other options by clicking on the right side, and this is what it would have looked like if we'd have just used the vertical beam. Or the 4-beam average, which in this case is identical because we didn't have any invalid data that defaulted then to the vertical beam. One of the unfortunate things that can happen is that the automatic filter does not filter out some of the data that we might like it to filter out. And currently there is no way to manually mark that data invalid. And we really don't know what is down there unless we have field notes to tell us, that there's some sticks or trees or limbs or something in the way, and we might be better off with a deeper depth along this area. So this is where the depth tab can provide some insight into what is actually going on and also filter out some obviously invalid depths. If we look at the second tab, we see a situation where the filter works as expected. We're getting very consistent data along the main channel, and then we get one deep spot. So that spot gets filtered out. This is where the smooth filter works very well. However, near these edges on this particular measurement, perhaps again because they're beginning to come up into some of the overbank and get into some vegetation, the filter really struggles. We will continue to use this second measurement as it also provides a better example to illustrate some of the features in the water track tab. Like the other tabs, the water track tab has a table at the top, but in this case it shows the number of depth cells rather than just ensembles. So it's the number of each individual depth cell. So this transect has over 4,800 depth cells. And then the percentage of invalid data due to the various filters. The filters at the right, you'll see 3 are very familiar. They're essentially the same filters that were used for bottom track, for 3-beam solutions, for air velocity, and vertical velocity. However, there are 2 additional filters. The first is the excluded distance below transducer. This filter is set automatically by QRevInt for M9s, which is equal to 16 centimeters, and for RioPros, which it sets equal to 25 centimeters. This is the distance below the transducer where the data will be marked invalid due to the potential for interference from flow disturbance as flow moves around the ADCP. The other new filter is a signal-to-noise ratio filter. This filter is only active for Sontec ADCPs, and it is a measure of the spread of the signal-to-noise ratio between the beams used for water tracking. The radio buttons along the top of the plot, again, look very familiar. They essentially correlate with the filters on the right. If we look at beams used, again, for Sontec, we'll see that it's always a 4-beam solution. If we look at air velocity, we collected data with 3 different water modes. Green being a 1 megahertz HD mode, the magenta or purple being a 3 megahertz HD mode, and the orange or yellow pluses being a 3 megahertz incoherent mode. One of the things to note is right in the middle of this 1 megahertz HD, it switched to 3 megahertz HD. If we zoom in on that, we can see that for 2 samples, it switched modes and then went back to the 1 megahertz HD. And when we look at the color contour plot, we can see the change in size of the cells when you change from 3 megahertz to 1 megahertz. This change in depth cell size is also clearly evident where we have 3 megahertz incoherent compared to 3 megahertz HD mode. When we look at the vertical velocity, we see that there are a couple of points that have been marked invalid. That may seem unusual because if we zoom in, we can see that those points are well within the spread of the 1 megahertz HD points. However, if you recall, when we're using the automatically applied filters, they are applied to each type of cell or mode of operation. So the filter is applied only to 3 megahertz HD. So these particular depth cells are associated with these depth cells in the computation of the filter thresholds. Because there is much less spread in these, there's a couple of depth cells here that exceed the computed threshold and are therefore marked invalid. If we change the filter to manual mode, then the thresholds are applied independent of the frequency or water mode used. Finally, if we look at the signal-to-noise ratio, and we click down to the third transect, we see that we have one signal-to-noise ratio that exceeds our threshold. Our threshold is 12 dB, so if the range between all of the beams exceeds 12 dB, then that particular ensemble is marked invalid. And this is different from the other plots where each of these represented an individual depth cell. For SNR, each point represents the entire profile. And like in the other tabs, we can choose to compare the ship track for GGA, or VTG, or turn the vectors on or off. in evaluating our data. Now let's discuss how interpolation is applied for water track data. Water track data are different from bottom track, GPS, and depth data, which are essentially one-dimensional time series data, and can be easily filled in using linear interpolation. However, for water track data, the data are effectively two-dimensional, having both a depth within an ensemble and then neighboring ensembles. So the interpolation that is used is referred to as ABBA, above, below, before, and after. For this example, we've identified our cell that has invalid data and highlighted it in red. This becomes our target cell. We first look above the target cell to find the first valid depth cell above it. Then we search below it to find the first valid depth cell below it within the same ensemble. Then we look at the ensemble before and identify all depth cells that overlap our target depth cell. Then we look to the ensemble after and identify all depth cells that overlap our target depth cells. We then compute the distance between the center of our target depth cell and the center of all the cells that neighbor our target depth cell. Inverse distance weighting is then used to compute the value of each velocity component for our target depth cell. In the case where we have an invalid cell immediately above our target cell, the algorithm would continue to look for a valid cell in that same direction above our target cell. And when it is identified, if any, it would then use that cell. It would continue to have an influence on the value of our target cell, but because the distance is now larger from the center of our target cell to the center of our next valid cell, it would have less influence on the value than those immediately surrounding our target cell. Similarly, if we have a whole ensemble that's invalid next to our target cell, it would continue to look in that direction until it found overlapping depth cells. And again, these depth cells would have influence on the value for our target cell, but they would have less influence because they are now further away from the center of our target cell. Again, the interpolation is applied to each of the two components making up a velocity. The north component and the east component, or if you prefer, the U component and the V component. The quality assurance indicators for bottom track, GPS, depth, and water track are the same, and they are based on the effect of the invalid data on the discharge. So, for a caution or yellow color, if the interpolated discharge is greater than 10%, or the interpolated discharge for consecutive ensembles is greater than 3%, that caution will be issued. If the interpolated discharge is greater than 25%, or the interpolated discharge for consecutive ensembles is greater than 5%, a red or warning will be issued. And that concludes this session covering bottom track, GPS, depth, and water track tabs.